Hi, I'm Dr. Jacobi, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the Schrodinger's time-independent wavy. So, Schrodinger's time-independent equation, so it is developed, that is, Schrodinger developed a differential equation which gives the solution that yields possible wave functions that can be associated with a particle. So, de Broglie have been given that lambda is equals to h by p. So this is the relation between, that is a particle as well as wave nature of the particle. So a wave is associated with a particle. So lambda is the wave nature, and p is nothing but momentum. So which is a characteristic, which is a feature of the particle. So that lambda is equals to h by p. This was given by the de Broglie for a matter wave. Matter wave is nothing but a wave which is associated with a particle, that is dual nature of a wave. So here Schrodinger developed a differential equation so that gives the solution for the possible wave functions, so which is associated with a particle. It can be associated with a particle. So this equation tells how the wave function changes as a resultant force acting on the particle. So that is in wave. So suppose if we tell that a wave, it is not a single wave, there is a group of waves there. So when there is a force acting on a wave, so what will be the resultant force? So and when the resultant force is acting on the particle, how the wave functions will be changes. So this equation tells that kind of information. That is, this equation gives how the wave function changes according to the resultant force acting on the particle. So one of the waveform can be derived by taking de Broglie wavelength expressions. So one of the waveform is deriving by the consideration of de Broglie wavelength expression. So here we are taking a particle of mass m, a particle of mass m which is moving with a velocity v, and it is associated with a group of waves. Suppose here we are taking a particle of mass m and it is moving with a velocity v. It is associated with a group of waves. Then let psi be the wave function. Let psi be the wave function of the particle, and also considering the simple waveform of wave equation. That wave equation is psi is equals to psi naught sine omega t minus kx. So here if we take that is if we take three coordinate system, so psi of x, y, z, t. So psi is a function of position and time. Psi is a function of position and time. So here we are considering three coordinates, so that psi of x, y, z, t is equals to psi. So here the simple form of the wave function, which is considered as the simple coordinate, that is one coordinate as x. Okay, psi of x. So psi of x is equals to psi naught sine of omega t minus kx. So that is we are taking psi of x is equals to psi. So psi is equals to psi naught sine of omega t minus kx is a simple form of wave equation. So where here psi naught is amplitude and omega is the wave velocity, T is the time and K is the vector constant. This vector constant is 2 pi by lambda. The value of vector constant is equals to 2 pi by lambda. So on partial differentiating the equation, that is simple equation, which is psi is equals to psi naught sine of omega t minus kx. So partially differentiating this equation with respect to x will get dou psi by dou x is equal to minus k psi naught cos of omega t minus kx. So how we are getting this partial differentiating solution for simple waveform psi is equals to psi naught sine of omega t minus kx is, so where d by dx sine x is equals to cos x. So here we have d by dx of sine kx sine kx, so it is equals to cos kx cos kx. So here we have minus kx, so that cos kx minus k. So here we are getting psi dou psi by dou x is equals to dou psi by dou x is equals to minus k psi naught cos omega t minus kx. So this is the dou by, that is dou psi by dou x. As here we are taking time independent wave equation, so t we are taking as a constant, so that we are taking sine of minus kx. So in this case d by dx is equals to d by dx of sine of minus kx. So the solution sine of kx, that is sine x is equals to cos x. So cos x d by dx of minus kx. So that is equals to cos x into minus k. So that minus k cos x, like that it will come. So here when applying to this equation, we'll get psi is equals to psi naught cos omega t minus kx. So minus kx. So that is not kx, k minus k. So it is equals to minus k psi naught cos of omega t minus kx. So this is the partial differential equation solution for the simple wave equation psi is equals to psi naught sine of omega t minus kx. So again we are partially differentiating with respect to x, will get dou square psi pi dou x square is equals to minus k sine of dou by dou by dou x of cos of omega t minus kx. So it is equals to minus k sin naught. So this will come minus sine of omega t minus kx and dou by dou x of minus kx here, that is minus k. So it is equals to minus k sin naught minus place, so that sin omega t minus kx into k. So it is equals to minus k square sin naught sin of omega t minus kx. So likewise we are getting here the value dou square psi by dou x square is equals to minus k square sin naught sin of omega t minus kx. So dou square psi by dou x square is equals to minus k square psi. So psi is nothing but sin naught sin of omega t minus kx. So substituting psi instead of psi naught sin of omega t minus kx. So dou square psi by dou x square is equals to minus k square psi. So dou square psi by dou x square plus k square psi is equals to 0. So we are taking simple form of a wave function. So as a wave function, psi is equals to psi is a function of position and time. So position and time when taking three coordinate system, psi of x, y, z, t is equals to psi. But we are taking simple form of wave equation, so which is in one dimension. So psi of x t is equals to psi. But here t is constant, so that we are taking psi is equals to psi naught sin of omega t minus kx. So this is the simple wave equation in one dimension. So here we are doing partial differentiating. So dou psi by dou x is equals to psi naught dou by dou x sin of omega t minus kx. So psi naught, so sin x, so sin x value is cos x, so that cos of omega t minus kx, but here t is constant and here minus kx is there, so that dou psi by dou by dou x of minus kx will get minus k, so that minus k sin naught cos of omega t minus kx. So this is the equation solution for partial differential of wave function. So dou psi by dou x is equals to minus k sin naught cos of omega t minus kx. Again partially differentiating. With respect to x, so dou square psi by dou x square is equals to dou by dou x dou by dou x to minus k sin naught cos of omega t minus kx. So minus k into sin naught dou by dou x cos of omega t minus kx. So it is equals to minus k sin naught cos x cos x dou by dou x of cos x is minus sin x. So minus of omega t minus kx into d by dx of minus kx is minus k. So minus k sin naught k sin omega t minus kx. So we cancel, so that minus k square sin naught sin of omega t minus kx. So this is the equation of dou square psi by dou x square. Dou square psi by dou x square. But here this sin of omega t minus kx. So where sin naught into sin of omega t minus kx is equals to psi. So that instead of sin of omega t minus kx, we are replacing with psi. We are substituting with psi. So dou square psi by dou x square is equals to minus k square into psi. Minus k square into psi. So that dou square psi by dou x square plus k square psi is equals to 0. When we said that k is the vector constant and its value is 2 pi by lambda. So let's substitute the value here. Substituting k value in this equation. So dou square psi by dou x square plus here k value is 2 pi by lambda, but k square is equals to 4 pi square by lambda square. So 2 pi by lambda square to psi is equals to 0. So dou square psi by dou x square plus 4 pi square by lambda square into psi is equals to 0. So but here, so lambda, we are taking de Broglie wavelength equation. So lambda is equals to h by p. So substituting de Broglie wave equation, lambda is equals to h by p in this equation. So lambda square is equals to h square by p square. H square by p square. So dou square psi by dou x square plus 4 pi square by lambda square is h square by p square. So h square by p square into psi is equals to 0. So dou square psi by dou x square plus 4 pi square p square by h square into psi is equals to 0. So dou square psi by dou x square plus 4 pi square p square by h square into psi is equals to 0. So here p is the momentum. So momentum is mass into velocity. So p is equals to mv. So let's substitute p square value m square p square in this equation, so that dou square psi by dou x square plus 4 pi square p square is m square v square divided by h square to psi is equals to 0. But h cut is equals to h by 2 pi, which is reduced Planck's constant. H cross is equals to h by 2 pi. So implies h is equals to 2 pi h by 2. So h square is equals to 4 pi square h cross square. So let's substitute in this above equation. So dou square psi by dou x square plus 4 pi square m square v square by 4 pi square 4 pi square h cross square into psi is equals to 0. So, so 4 so here dou square psi by dou x square plus 4 cancel 4 pi square so that m square v square by h cross square into psi is equals to 0. Okay, so dou square psi by dou x square plus m square v square by h cross square into psi is equals to 0. So this is equation 5. So now we are taking energies. So the total energy of the particle is E. So that the total energy is the sum of kinetic energy and potential energy. So that kinetic energy is K and potential energy is V. So total energy E is equals to K plus V. So K is half mv square. So E is equals to half mv square plus V. So this implies kinetic energy K is equals to A minus V. So half mv square is equals to A minus V. So we want in terms of momentum so that multiplying with m on both sides. So we'll get half mv square is equals to A minus V into m. We are also multiplying with m so that half m square v square is equals to m into E minus V. So we need momentum so that m square v square is equals to, so these two I'm taking into other side. So 2m into E minus V. So let's substitute this equation in the fifth equation so that we'll get so dou square psi by dou x square plus m square v square value is 2m into E minus V. So divided by h cross square into psi is equals to 0. So this is called the Schrodinger's time-independent wave equation for one-dimensional, which is for x coordinate, and for three-dimensional, we'll take all the three coordinates. So here, so here, so dou square psi by dou x square plus m square v square by h cross square psi is equals to 0. In this case, we need to find the momentum. We need to find the momentum m square v square so that we will get from the energies. So that we are taking total energy. So total energy E is equals to E is equals to kinetic energy plus potential energy, but we know K is equals to E minus V. So K is half mv square is equals to E minus V. But here half mv square, so we need in terms of momentum so that multiplying both sides with m, so m into half mv square is equals to m into E minus V. So that half mv square is equal m square v square is equals to m into A minus V. So we need m square v square so that m square v square is equals to 2m into A minus V. So this expression is substituted in the dou square psi by dou x square plus m square v square by h square to psi is equals to 0. So then dou square psi by dou x square plus, so the value of m square v square is equals to 2m into a minus v. So 2m into e minus v divided by h square to psi is equals to 0. So this is the equation for the Schrodinger's time independent. So which is in terms of energies. In terms of energies. If the potential value, potential energy is 0, if V is equals to 0, then the equation becomes d square psi by d dou x square plus 2me divided by h square into psi is equals to 0. So this is the equation for the one dimensional. Okay, so this is the Schrodinger's time independent wave equation for one dimensional, which is for the coordinate x. So if we want to find a three-dimensional, then so we'll take dou square psi by dou x square divided by dou x square, dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2m into e minus v by h square into psi is equals to 0. So for all three coordinates, so the three-dimensional Schrodinger's time independent wave equation becomes as dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 2me minus v divided by h square into psi is equals to 0. Where we know that psi is a function of x, y and z. So here this is the time independent wave equation. That's why we couldn't find the time t here. So as in the first itself, we have taken time as a constant. So we have taken psi of x. Okay. So as t is a constant, so that we partially differentiating by keeping the time as a constant, and we did the derivation. So in simple form, the three-dimensional Schrodinger equation. So taking as Laplacian operator, we'll write in the simplest form. That is the three coordinates. That is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. So dou square by dou x square plus dou square by dou y square plus dou square by dou z square into psi. So here this can be taken as Laplacian operator del square. So del square psi become del square psi. So the final expression is del square psi plus 2m into e minus v by h square psi is equals to 0. So this gives the Schrodinger's time independent wave equation for three dimensions. So where here the psi represents time independent states. Time independent states. Okay. So this is Schrodinger's time independent wave equation, which is which gives the wave function, how the wave function is changed when the resultant force is changing, or a resultant force is acting on the particle. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.